Yeah, good morning, my dear students. Good morning. Nice to meet you all today. Okay, just I will project the notes and discuss today class. Right. Actually, last class I have done this problem. We have seen problems on two-way slabs, right? In two-way slab, this problem complete problem we have seen how to do the design. Okay, what is the difference between this problem and the next problem which I am going to discuss with you? What is the difference between them? Actually, it is a two-way slab, but simply supported. All around the slab is simply supported. It means it is not only simply supported, the corners are not held down case. Corners are free. The uplifting action at the corners is permitted, not restrained, not constrained. They can uplift. That is why we didn't concentrate on design for negative reinforcement. Okay, tension top no, at the corner. That reinforcement design we have not done. Only the reinforcement, okay, positive reinforcement at a shorter span, along shorter span, along larger span, okay, long span. That alone we have done. That design alone we have done. Hope you will understand, okay? Because the bending moment along short span, along long span we computed, and the necessary checks and all we have done. Finally, we determined the area of steel only for short direction and long direction, that to positive reinforcement at mid span, no, that we have determined. That's all. And then again we carried out the necessary check. Okay, for serviceability requirement, we have seen the check. That's all. With that, we completed that problem. Next problem in two-way slab, one more problem I am going to discuss with you. That is design of restrained two-way slab with UDL. Okay, we are going to design a two-way slab under UDL, live load. Okay, and it is restrained. Restrained means the corners are held down case. The previous problem was corners are not held down case. This problem is corners held down case. Okay, if the corners are held down, you have to refer the table available in Annex D to get the bending moment coefficient. Okay, based on the case of the slab you are designing. Suppose all the four edges are continuous. No, only two adjacent edges are continuous, while the other two adjacent edges are discontinuous. Likewise, there are cases I told you, no, in a two-way slab. The end condition, okay, based on the end condition, there are cases. So the slab which you are designing belongs to which case? You have to take refer the table available in Annex D. Accordingly, you have to refer the table, okay, and take the bending moment coefficient. Here you are going to calculate both the positive bending moment and negative bending moment. That is bending moment at midspan, bending moment at a support, at a continuous support, discontinuous support, like that. You are going to calculate, okay. Moreover, the corners are held down. That's why negative reinforcement also you are designing. So that is the difference between this problem and previous problem, okay. Design of restrained two-way slab with the UDL. Very good. A room 17.5 meter by 10 meter. Okay, see, such a big a room 17.5 meter and by 10 meter. Okay, has brick walls all around. Okay, very good. Sir, is it the size of the slab? No. How can we provide such a big size of slab? Let us listen. Okay, we will go through further in this problem. Has brick walls all around, and it is to be covered with a reinforced concrete slab. Okay, the room has to be covered with a reinforced concrete slab supported on the walls. Okay, and on the central beams in east, west, and north, south directions along the middle of the room. Okay, so you have a room, four walls are there, whose internal size is 17.5 meter by 10 meter. Okay, this room has to be covered with a reinforced concrete slab. Okay, but in this slab there is a central beam provided. Okay, in the east-west direction and north-south direction, means at the middle of the room, in both the direction, mutual perpendicular direction, beams are provided. Okay, that is the meaning of it. East, west, and north, south direction along the middle of the room. The slab has to carry a live load of 4 kN per meter square. Very good. The load is given as 4 kN per meter square, a slightly heavy load. Usually for residential building, we take the 3 kN per meter square or 2.5 kN per meter square. If it happened to be office building, 3.5, okay. But 4 is it's a slightly higher live load, 4 kN per meter square. Assume mild exposure condition. Okay, this is not necessary. Why it is given now? What should be the minimum cover to be provided to the slab to decide that? If the slab is exposed to mild exposure condition, 15 mm minimum cover required. Aggressive environment, cover should be slightly even 20 mm or something like that. There are codal provision, okay? But for that purpose, this is given. If it's not given also, doesn't matter. Assume mild exposure condition, and that M20 concrete, okay? Concrete is M20 with the Fe415 steel is used for the construction. Very good. Normally, we use only M20 concrete only in our slabs. M25 we prefer for columns, okay? M30 and all for M25, M30 and all for columns. Sometimes for slab also M20 or M25. Especially for columns, M30 only normally in practice we have been using. Okay, remember. The slabs are restrained on top of the walls by the brick masonry built about it. Design the slab, okay? The slabs are restrained on top of the walls by the brick masonry built above it. It means what? The corners of the slab is held down. That is the meaning. That it belongs to that case. Corners are restrained, constrained, held down. Okay. So the uplifting action is restrained. At the corners, the slabs are not allowed to uplift. Means they are going to be torsional effect there at the corners. Negative bending moment will be there at the top. Tension will be at the top. So you have to design reinforcement along the edges. Negative reinforcement you have to design, and you have to take care the reinforcement details at the corners. Torsion steel, corner steel required to be provided. Keep it in mind. Okay, we will discuss this problem further. Whatever manner it is discussed, you try to follow it in your own way. Okay, you try to write down while taking notes in your own way. Right. Now this Lx is equal to 5 meter. How? See here, it is 17.5 meter by 10 meter room. No. Now, in that there is a middle beam is there in the slab. It means what is the 1/4 size of the slab? 1/4 size of the slab is half of this, half of this. Okay. So 17.5, what is the half? 8.75. Okay, 8.75. 10 meter, what is the half? 5 meter. So 8.75 by 10 meter is the quarter size. Okay. So there are four slabs are there likewise. Okay, two-way slabs are there in that. Therefore, Lx, Ly, because there is a centrally beam is run east, west, north, south direction. There is a beam available. The slab is resting on it, on those beams, and the wall around it. Okay, that's why the slab is supported like that. No, so that is each size of the slab you have to design. Lx is 5 meter. Short span is 5 meter in each. Long span of the slab is 8.75. So what is the Ly by Lx ratio? Obviously, it is less than 2. Okay, it belongs to a two-way slab, no doubt. Cover for mild exposure is 15 mm. That is well cover. The nominal minimum cover should be 15 mm for mild exposure, no problem. Next, assume span to effective depth ratio. Span to depth ratio, I use code, it is available. Okay, we have seen several times. Normally, the span to effective depth ratio ranges from between 25 to 40. Okay. 40 we took 80%. So we took 35, 38, 32, anything. So this span to effective depth ratio, you are the decision maker. You can decide anything, but you cannot take some relevant value. Totally deviating, you should not take. Either you can make it 30 or 32, 33, 34, 35, 36, up to 40. You can decide anything from 20, anywhere between 25 to 40. You can assume this author has taken 32. Suppose you take 34, no problem, nothing wrong. Suppose, no, sir, I want to take 35, nothing wrong. Okay, no, sir, I want to take 30 only. No, you can, yes, you can go ahead. Okay, so any range, it should be in that range. The author has taken 32. Okay, we will discuss with this 32. So D equal to short span is 5000 mm. No, you see here you need not determine the effective span and all. Whatever size given, take it as center line distance. Okay, so you can proceed with that. No, sir, whether is it necessary for me to determine effective span? No, not necessary. Okay, with the span, because what is effective span? Clear span plus that thickness of a wall, or clear span plus effective depth of the slab, whichever is less is the effective span. Still, we have not decided anything about the depth of the slab. No, that is why you need not bother about the size. Whatever given, you can take it. So 5000 is the short span, and okay, that would be 32 is equal to 156 mm. Okay, Since you have got immediately the author has not decided. Okay, provide 150 mm, take D equal to 150 mm, he has not decided. He has decided assume H equal to 180. He has done like that. Normally, if you take this is as 150, what will be the total thickness of the slab? 150 plus 5. Okay. Suppose if you want to use 10 mm diameter steel bar, 150 plus 5 plus 15 mm. 20 you have to add. Okay. So 150 plus 20, 170 mm thick it will be. But the author has decided H equal to 180. No problem. Suppose if you proceed this way, nothing wrong. If you suppose you are computing 5000 by 32, 156, say 150 mm, let the effective depth D equal to 150 mm. If you take, no problem. Suppose you want to use 10 mm dia bar in your slab. Okay, center of the reinforcement 5 mm, no 5 mm, 5 mm 150 plus 5 plus 15 mm clear cover is equal to 170 mm. That is the thickness of my slab. If you say nothing wrong, correct, 100%, that also right, you can proceed. Finally, your whatever geometrical value you assume, finally everything should be safe. Okay, everything should be, the check should be satisfied. If any problem happens in the check, negative effect if you get in the check, you have to redesign. Okay, you have to redo the problem. That's all. Otherwise, you can write down the slab has to be redesigned by changing the so and so data. You can complete it. During exam, you will not again do once again. No need. You can write and conclude. Okay. But the author has taken 156. Then what he has designed, overall thickness 180 mm. In that he deducted minus 15 minus 12. Okay. Why he has deducted minus 12? See here what he has done. This effective depth he has taken for the, it's a two-way slab, no? There is a bottom main reinforcement, top main reinforcement. To the top or the center of top reinforcement, he has taken this. See, this depth equal to 150 mm, anything you can decide. That's what I want to say. Okay. So the author has taken depth of the slab 180 mm. See, please listen here. In practice, whatever slab we use, normally 100 mm, 120 mm, 130 mm, 140 mm. Definitely, we never deal with the slab more than 150 mm in our usual design. Okay. There we will be using only 80 mm and 10 mm dia bars in our slab. We never prefer to use 12 mm dia bar in our slab. But in this problem, the thickness is happened to be 180. The author preferred to use 12 mm dia bar. Okay. So I will proceed with as it is, but keep it in mind. I will be redoing this problem. No, do it with the 10 mm dia only. Okay. And thickness also you slightly reduce. Take the overall thickness as 160, not 180. Okay. In that you deduct 15 and deduct 10 mm. And you will be getting the effective depth for the upper reinforcement. Okay. That way you calculate. I advise you to calculate. Right. I will proceed. Think over the problem. Okay. You draw the sketch and think over and then you do the problem. Okay. I will go to the problem. Okay. Dead load. Dead load equal to, since the author has taken overall thickness of the slab as 180 mm, 0.18 meter into 25. Here itself, I told you to write, consider 1 meter wide strip of the slab in short span direction. In short span direction, consider 1 meter wide strip of the slab. Write down and underline it. Then you can write 0.18 into 25 is equal to 4.5 kilonewton per meter you can write. Why? You have already considered 1 meter wide strip of the slab. Only for 1 meter wide 1 meter run, the load is 1 to 4.5 kilonewton. The dead load is 4.5 kilonewton per meter run of the 1 meter wide strip. That is the meaning. Okay. So you will not write a meter square here. Simply kilonewton per meter you can write the unit. Live load equal to 4 kilonewton per meter you can write. Why? 1 meter run of 1 meter wide strip. Because if you give heading here, consider 1 meter wide strip of the slab, you can proceed this way. Okay. Therefore, design load, factored load or design load is equal to partial safety factor for load. No, 1.5 you have to multiply. So if you multiply dead load plus live load multiplied by 1.5, 12.75 kilonewton per meter. W equal to 12.75 kilonewton per meter run of the 1 meter wide strip. That is the meaning of it. Okay. Hope you will understand. Okay. Every time you will not write for 1 meter square. The author has done like that. You do the other way, the way in which I tell you. Okay. And also now he is a type of slab he ascertained. LY by LX ratio he computed. he found 1.75, and it is a two-way slab. Okay, either at the beginning itself you can write down, or here also you can write down. No problem. Anywhere you can write down. That a two-way slab. Better I advise you to write down the slab is two-way. This one you show it here itself at the beginning. LY by LX ratio equal to 1.75. Hence two-way slab. You write there itself. Okay, in the beginning itself you write. And then he done some check for shear. I already told you approximately you can check for shear. You need not get the exact shear force coefficient exactly from the table. You need not choose. Approximately you can write 0.5 WL. Okay, 0.5 WL. W is this 12.75 kilonewton per meter into 0.5 WLX. The L should be X, short span, 5 meter, 5,000 mm. Okay, that you multiply. Approximately you calculate and determine what is the nominal shear. Tau V is equal to, you compute. Okay, shear force V by BD into 100. Okay, sorry, V by BD. Tau V, shear force equal to V by BD, you determine in Newton per mm square. And for M20 concrete, Tau C, design shear strength should be 0.36. Either M20, M25, okay, 0.36 only, 0.36. So the nominal shear stress is less than the design shear strength of the concrete in this slab. So hence shear reinforcement not required. For slabs, shear reinforcement not at all required. Okay, why that check is done now? The thickness of slab is 180 mm. That is why the author has done it. Okay, better to check it because you have to write some steps. No, better you can do check for shear also in your calculation. Now we are coming to the main part of the design work. Okay, bending moment, short span direction. We are going to determine shear force. Okay, sorry, bending moment. Write down bending moment coefficient design for steel. Okay, steel design. You can write down design for steel reinforcement. Give heading. Okay, short direction. First short direction you are going to deal. Give heading as short direction. M equal to no beta x, alpha x. Already you have formula, no? Mx is equal to alpha x W Lx square. That write down. Okay, M suffix x equal to alpha x W Lx square. Now this bending moment coefficient alpha x and alpha y required to be referred. Why this author has used beta x here? Na, if it is a two-way slab, semi-supported slab, na, easily alpha x, alpha y you can take. But here there are going to be two coefficient, positive coefficient and negative coefficient. That is why slightly he has used beta x. Even if you put alpha x, nothing wrong. Okay, beta x or alpha x, something you can put here. It's a coefficient. We are going to refer negative coefficient and positive coefficient. Both we are going to see. So negative on continuous edge. How do you refer it? For that you have to go to Annex D of your IS code. Okay, table 26. In Annex D of your IS code, this is given. See, our slab belongs to which case? See here, there is a brick wall. In that central beam is there. 1/4 slab only we are considering. That slab is continuous to adjacent edges. But it is discontinuous. It means what? The slab is resting onto adjacent side on the beams. On the beams, right, it's continuously. It is going to next panel. Next side also it goes. The slab is continuous in both direction to adjacent side direction. But it is discontinuous at a brick wall direction. Hope you will understand. The slab, there are 4 edges in the slab. 1/4 only we are considering. Okay, there is a central beam run. No, that is why the quarter portion we are considering. 2 adjacent sides are continuous, which are resting on the beams, while the other 2 adjacent sides are discontinuous because which are resting on brick wall. There the slab ends. Okay, discontinuous. So in which case it comes in this table? See, interior panel na, all 4 edges are continuous one. One short edge continuing alone case. One long edge discontinuous case, this one. 2 adjacent edges discontinuous. So our problem comes under 2 adjacent edges discontinuous case. While what it is meaning? 2 adjacent edges discontinuous, na, the other 2 edges are continuous one. The slab is continuous. That is the meaning. Okay. For this, negative moment at continuous edge, positive moment in midspan. The coefficients are given. So what is Ly by Lx ratio? We computed 1.75. So below 1.75, come to this case. Okay, 2 adjacent one. Negative moment at a continuous edge. See 1.75, 0.084, positive moment at midspan 0.063. That is the coefficient. This is for LX, short span direction. For MY, that is alpha y, no? This is alpha x. Alpha y for other values is here. Where is that? Two adjacent edges, here. 0.047, 0.035. Okay. Positive moment at midspan 0.035, 0.047. This is for alpha y. This is alpha x. Okay. Short span direction moment. This is for long span direction moment. This coefficient. This coefficient you have to use. Keep remember 0.063, 0.084. Let us see the problem. With this, I will finish just a few minutes. Okay. So negative continuous edge is equal to 0.084. We have seen, no? I hope you will be remembering. Okay. 0.084. We have seen this value. Okay. That's what 0.084 into load. Load is 12.75 kilonewton per meter into shorts LX square, 5 square. Okay. So 26.78 kilonewton wrongly given. It is not per meter, kilonewton meter into meter. Negative continuous edge moment, it's a moment. Okay. It is kilonewton into meter. It's wrongly printed in this book here. Positive at midspan is equal to 0.063. I told you, no, the coefficient, where it is 0.063. Okay. The positive moment at midspan 0.063 for LO by LX ratio 1.75. Okay. So therefore, it is written here 0.063 into 12.75 in 5 square equal to 20.08 kilonewton meter. So with this, they have not completed. Negative on discontinuous edge. At a discontinuous edge also, there is a negative moment. Why? Although it's a discontinuous edge, it's not a simply supported edge on which brick wall is resting. Okay, it is constrained. Not only the corners are held down, full edge is constrained. It's not simply supported because on the brick wall, the slab is resting, over which another brick wall is there. The upper floor brick wall is resting. That is why the negative on discontinuous edge is equal to 1/2 span moment. Your positive moment you are getting, no? Idhula vandu half. You have to take off 1/2 span moment. That is 20.08, 10.04 kilonewton into meter. Into meter. Wrongly printed in this book. Okay. 20.08 kilonewton into meter. Kilonewton meter. 10.04 kilonewton meter. They are moment. Okay. Why is this kind of printing mistake? Afterwards, okay. It's a good book. When very beginning when it was published, meanwhile, the author has not concentrated much on this. It's okay, but please correct them. Okay. Note in the note itself, it is mentioned. Note that negative moment, 4/3 of positive. The positive moment we obtained, the negative moment is 4/3 of positive moment, and at the continuous edges, it is half of the moment. That law you should know. This because to determine moment for other cases. Okay. Now I'm short span direction moments are over. See, okay, at a midspan, at a continuous end, at a discontinuous end. There are 3 moments we computed. Okay, along short span direction. Along long span direction, I am coming. With this, I will finish. Positive at midspan. Okay, 0.035. What is that? The coefficient is shown here, no? This here, 0.035, this coefficient. Okay, that into load 12.75 kilonewton per meter in our case into LX square, 5 square, equal to 11.16 kilonewton meter. Positive moment at midspan calculate pannite. Please, I advise you, next one, this negative on continuous edge, is straight away taken 4/3. Don't take like that. This coefficient you use, which one? 0.047. It is given here. 0.047, okay, into 12.75 into 5 square. You write down here instead of computing 4/3 of this in computing. Here he realized it is 4/3 of that. That is why here he has done 4/3 of this. Don't do that. Use the coefficient and compute. You will be getting 14.88 kilonewton meter. Here he given the correct unit. See, here the units are given correctly. There the author has done the printing mistake is there. Okay, here kilonewton meter moment. Negative on discontinuous edge is half of positive moment. Positive moment is midspan moment. Positive moment is here. in this off 5.58 kilometer meter. Okay, that's with this I will finish. Please see here, in along short span direction, 3 movement we computed. Along long span direction also 3 movement. What are the movement? At a mid span moment, positive moment, and 2 negative moment. One is at a discontinuous edge, another one is at a continuous edge. Okay. Likewise, in a long direction also 3 movement we computed. A positive bending moment at mid span, and a negative moment at a discontinuous edge, and a continuous edge. Okay. So totally 6 moments are there. For these 6 moments, you have to design reinforcement. Okay, you have to take each value one by one and do it. Okay, since many of the students are attending in-plant training, today full strength is not available. So I will stop with this half of the problem. The remaining half of the problem, I will continue in the next class. Okay, just I want to record your name. I know that majority of students are attending in-plant training. Okay, so they are not in a position to attend class, right? So just I will record the names of the student who are attending class today, right? Very good. Yes, seems to be very good. Okay, very good. Since majority of you are attending, no problem. I have recorded your name for attendance, right? Okay, good, nice. So I will stop recording. If you want to discuss anything, you will discuss. Okay.